Hello, everyone, and welcome to Algebra 2. This is section 5.6, the inverse of a function. Before we get to inverses, we actually need to understand something called the composition of functions. And before I can do that, I'm going to start just with basic function notation. So when you see f of x, you think of that as a general formula, probably. But when you see f of 3, you know that that means you want to put the 3 in where the x was. So you would get 3 squared plus 1, which is 10. If you saw f of heart, you would do heart squared plus 1. If you did f of smiley face, my point is it doesn't matter what's in the parentheses. That's what gets replaced by the x. So, or that's what replaces the x. So even if I did f of w, now you'd have to write w squared plus 1. But what if I wrote f of w minus 3? Then you would have to write w minus 3 squared plus 1. And what if I told you f of g of x? Well, I'd have to tell you what g of x was. But you could start by saying, well, I'm going to square g of x and then add 1. So now if I told you that g of x was 2x plus 3, then you would be able to say that f of g of x is 2x plus 3 squared plus 1. And that is called the composition of functions. And on the outside chance you didn't quite follow it, we're going to do a bunch of examples, but I think I like to start this way because I like you to see that all we're doing is what you've always done. Whatever you've seen here, you've plugged in, whether it's a variable or an entire expression, or now a whole another function. So let's go back to our problems. F of x is equal to 5x squared, and g of x is equal to 3x minus 2. I want f of. So as soon as I see f of, I think I want 5, and I'm going to replace the x with something. What am I going to replace it with? With g of x, 3x minus 2. This is actually a perfectly acceptable answer. If you did multiply it out, make sure you don't distribute the square. It would be 9x squared minus 12x plus 4, and then you could get 45x squared minus 60x plus 20. But I actually don't mind if you leave this answer. This is a really tidy answer, but just make sure you don't distribute the square. On this next one, it says g of. Okay, as soon as I see g of, I'm going to write 3, and I know I'm going to replace my x with something. What am I going to replace it with? With f of x, which is 5x squared. This one you should simplify, not much, just make it a little tidier, 15x squared minus 2. And the last one, f of x. So I see the f of, and I'm going to write the f equation, f something squared. I know I'm going to replace that. And it's a little crazy, but what am I going to put in that parenthesis? F of x, 5x squared, which gives me 5 times 25x to the 4th. You can distribute the square when it's multiplication, just not when it's addition. And that gives me 125x to the 4th. All right, there's 3 more that you can try on your own if you want to, but of course I will do them out. First one, f of, and actually, I'm not going to do that first. I think it would be much easier to rewrite this as 3 over x. Remember that a negative exponent on the top is a positive exponent on the bottom. So f of, and then whatever the of is going to go down here in the denominator. And it's g of x. So 2x plus 1. G of, so as soon as I see that, I'm going to do 2 times something plus 1. And then I put the f of x in there. 3 over x. Remember that when you're doing a whole number times a fraction, it's easier if you change the whole number to a fraction and do a fraction times a fraction. And then the last one, f of, so 3 over, and then 3, f of x, which is 3 over x again. So I will show you how to do this. It's not hard. And then I'm going to show you a second way. So if you have a number or a fraction divided by a fraction, you want to keep the first one. You want to change this division to multiplication, and then you want to flip. People call it keep, change, flip. I actually was taught flip and multiply, but that's okay either way. Now you get 3x over 3, which is just x. Interestingly, on this one, 3 over, instead of 3 over x, this one actually would have been easier to leave in the original form. Not for the first one, but for the inner one, because then you could have canceled the 3's, and then you could have moved the x to the numerator. Because it is a negative exponent, you can move it to the numerator and make it positive. But notice you get the same answer either way. So whichever one makes the most sense to you. Okay, there's one last set of practice problems. So if you still haven't stopped this video and tried on your own, I highly recommend you do so now. F of, so 2 something to the 1/5. What goes into something? G of x goes in there. You do have to remember your laws of exponents. Do you multiply exponents or add when they're being raised to a power? You do multiply. So I'm trying to do a number times a fraction. It's easier to make the number into a fraction, and then I get 3/5. The next one, g of, so something cubed, f of x, 2x to the 1/5. But now, be careful, now the 2 is also being cubed. It wasn't up here, that 1/5 only affected the x cubed. But now the whole thing is being cubed, so I get 8x to the 3/5. And last one, f of, so 2 times something to the 1/5, and f of x. So I'm actually going to put f of x itself back in where the x was. This one's a lot harder because that 2 also has to be raised to the 1/5. And then 1/5 times 1/5 is going to be 1/25. And then I would like you to simplify this. They have like bases. You can give them a common exponent. So, or I should say a single exponent. So 2 to the first times 2 to the 1/5. I want to add those. So how do you add 1 plus 1/5? Well, it is 1 1/5. But we don't do that in math. We don't use mixed numbers for fractional exponents. So I'm going to change that to 6/5. And if you didn't know how to do that, you can either do 5 times 1 plus 1 is 6. That's probably how you were taught in elementary school. Or when you were back at this step, you could change the 1 to a 5 over 5 to give it a common denominator. But either way, you'll get 6/5. Alternatively, I have seen students rewrite this as 2 5th roots of 2. So they just change that to fraction root notation, and then either x to the 1/25 or the 25th root of x, because they figure that way they've simplified it. It really doesn't matter. There's lots of good ways to write these problems. Okay, so number 4 is a little bit fun, if I can say that in math class, because now you have to think of the f of an x and the g of x that created that answer. So f of x, I'll do the first one for you just to explain what I'm talking about. So f of x, I can see is something cubed. So I'm going to say x cubed. And then what did they put inside there? G of x? They put in 6x minus 5. Right? Let's talk about that. F of g of x is something cubed, right? Because f of And then what goes in there? G of x. And G of x, I said, was 6x minus 5, so it checks. It definitely works. You should try the next two on your own. Of course, I'll do them for you. F of x is equal to the absolute value of x. Think of it as the outer function. And then G of x is 2x plus 9. It's the inner function. And the last one, F of x is equal to, so you might be inclined to say x over 2, and then G of x, what do we want to replace that with? We want to replace that with the fourth root of x. There are more than one answer. You don't have to do these all the same, or they'll probably say answers may vary in the back. So here's another thought. Maybe somebody had f of x is equal to the fourth root of x, and then g of x, this one would be much harder, would be x over 16. Let me check that and make sure that actually works. So f of g of x, x over 16. That would give me the fourth root of x over, and the fourth root of 16 is 2. So, you know, there's more than one way to do it. You can find a way that works for you. Word problem application. A clothing store advertises that it is having a 25% off sale. For one day only, the store advertises an additional savings of 10% off. Write an equation that could be used to determine the sale price. So you need to know that additional means after they've taken the 25% off. So let's say that the price of the clothing is X. How do we find 25% off? So 25% as a decimal is 0.25, and 25% of, the word of always means times, 25% of X, so times the original price, will give you the discount. So if you want to figure out how much you're going to pay, then you're going to pay X minus 0.25X. Here's your original price. Here's your discount. And so remember, this is a 1. 1x minus 0.25x is 0.75x, which, by the way, should make sense, because if you're not paying 25% of the price, you are paying 75% of, remember, of means times, you're paying 75% of the price. And then they're going to give you an additional $10 off. So they're going to take that 0.75x, whatever it is, and then they're going to subtract $10, and that is going to be your S, sale price. So what would be the sale price of a $40 sweater? So the sale price of 40, that's the notation that we use, is going to be 0.75 times 40 minus 10, and that comes out to be $20. Good deal. Ends up being half price in this particular case. So I realize we still haven't gotten to inverse functions, but it's all leading up to it, I promise. So these 4 graphs is definitely to introduce inverse functions, but they're also to help you practice graphing. So if I were in the room, I definitely would not show you how to graph these. I would let your group remind themselves how to do graphs. So if I were you, I would stop, I would make the graphs, but of course I am going to do it for you. So this is a line. Its y-intercept when x is 0 is 3, so I know it passes through the point 0.03, and I know it has a slope of 4. 1, 2, 3. Ooh, I can't quite make that, so I'm going to go down 1, 2, 3, 4, and back 1. 1, 2, 3, 4, and back 1. And that is what that one looks like. This one is just written in a difficult form, divided by 4 like that. So instead, change it to x over 4 minus 3 over 4, or if you really want to see the slope, 1/4 x minus 3/4. Now you may recall from the beginning of the year that you may not start at 0, 3/4. I do not want you to try and start here and go down 1 and over 4. Oh, sorry, up 1 and over 4, which is the slope. It's too tricky. You must find some of you got really good at this. One good point, but some of you never got this. So now you are a lot more mathematically skilled than you were 6 months ago. So let's talk about how to find one good point. So I would use this and just ask yourself, what number could x be that when you subtract 3, you're going to be able to divide by 4? So as an example, 7. 7 minus 3 is 4 over 4 is 1. Okay. Another one would be minus 1. Minus 1 minus 3 is minus 4 over negative 4 is negative 1. And of course, there's a nice easy one. 3 minus 3 is 0, and 0 divided by 4 is 0. So now you actually have enough. You could just plot the points. Actually, I can't really quite plot 7. Negative 1, negative 1. And again, the slope is up 1 over 4. You just need one good point to start. If you had started at any one of these points and gone up 1 over 4, it would have worked. But do not start at negative 3/4. Okay, next two graphs. X cubed plus 1. So I'm going to make my origin here, and the points you should have memorized for x cubed are 0, 0, 1, 1, negative 1, negative 1. And if you can fit it to 8, which I can't, but I can on this one, negative 2, 1, 2, 3, 4, 5, 6, 7, 8, I guess not. But it does give me a little bit of assistance in making sure that I graph it pretty accurately. X cubed minus 1 means it's going to go to the right one, not left. Remember, inside the function is opposite. Outside the function moves vertically. So I'm going to go to the right one, and its points are also 0, 0, 1, 1, negative 1, negative 1. And this is why the 8, 2 is so important, because cubic functions go up, but these go side to side. So down 2 and over 8, 1, 2, 3, 4, 5, 6, 7, 8, didn't quite make it. And again, this one's not going to quite make it either, but we know it's over there. And we need that just to get a sense of the shape. I hope you're doing these on your own and not just watching me. Square root graph, unless you need the graphing help. This is also going to go right 3. And from here, the points I want you to have memorized are 0, 0, 1, 1, 4, 2. Looks like that. And then my parabola is been moved up 3, but not left or right. There's nothing left or right here. It's just x squared plus 3. So I'm going to go up 3, 0, 0, 1, 1, 2, 1, 2, 3, 4. And I would normally reflect that, but it only wants me to do it for x is greater than or equal to 0. So I'm actually going to go like that. And the last one are lines again. So this goes through the point 0, 4. So I can start at 4 and go up 1 over 3 and make that line. And then this one, I can't start at negative 12. So again, what do? I need to find one good point. Do not try to start at negative 12 and then make the graph. Just find one good point. So try 1. Well, if you do 1, you'll get negative 9. So if 0 made negative 12 and 1 made negative 9, what do you need? A bigger number. So you could do 2, negative 6, or 3, negative 3. So 1, 2, 3, 1, 2, 3. And then once you have that, then you can go ahead and make your line. Always find one good point. Okay, so what do you notice about all these graphs? Do you see anything about them? Well, what you're supposed to be seeing, whether you see it or not, is that they all have a point where they cross. Well, actually, I don't think they all have a point where they cross. But if they do, that point falls on this line, which is a very special line. So this one's right there. This is the line y is equal to x. Go ahead and see if you can draw y is equal to x on all four of them. Okay, so these two didn't touch, but they still reflect over the line. I'm so bad at drawing lines without making dots first. It helps me. Y is equal to x. And this one's way up there, but it still is symmetric around this line. Y is equal to x. So whenever two functions reflect each other over the line y is equal to x, we call them inverse functions. Algebraically, they can be found by switching x and y. So if I were to make a table of values for this one, it would be exactly the opposite of that one. -9 would give me 1, and -12 would give me 0. And sure enough, it does. 1/3 of -12 is -4, plus 4 is 0. So inverse functions graphically reflect over the line y is equal to x. On the table, they switch all the x and y's, and they have a relationship on their functions. So square roots, the inverse of squares. Cube roots, the inverse of cubes. And steep lines with a slope of 4 have an inverse of a shallow line with a slope of 1/4. This one, slope of 1/3, slope of 3. So what we're going to do now that you understand what an inverse function is, we're going to go ahead and find some inverse functions. So this is a line, so I can picture it. We're just going to make a really quick sketch. It's somewhere around 3, and it has a slope of 2. So I know that mine is going to have to reflect that. So if this is the point 0, 3, I know 1 point on this. I know this is going to have 3, 0. And then it's going to have a shallower slope so that it reflects over that line. But you don't actually have to do that to get it. Here are going to be the steps. Step 1, replace f of x with y. Step 2, switch x and y. Just like we switched these as ordered pairs, x became y and y became x, we're going to do that in our equation. And then step 3, solve for y. So x minus 3 is equal to 2y. And then x minus 3 over 2 is equal to y. And so you can see that it is this equation. I am going to rewrite it as 1/2 x minus 3/2 is equal to y. So you can see the slopes were like that. Oops, I do not want to box that yet. And then step 4, this is the notation you're going to want to use, f inverse. You can't just call it y. They asked for the inverse function. So the correct notation for that is f inverse. It's not a -1 exponent. I assure you, if I had been in charge, I would have not have used the same symbol for inverse as I use for a negative exponent. But unfortunately, that is what somebody decided to do. So that means f inverse. So step 4, rewrite it. And it doesn't matter if you leave it like this or not, or like this. But you do need to write f inverse of x. All right, you can try the next 3 on your own, or you can wait for me to do them. So step 1, replace y with the f of x with y. Step 2, we change the x and the y, flip them. X is equal to 2y squared. Step 3 is to get y all by itself. So I'm going to divide by 2 is equal to y squared. And then this is ironic. What's the inverse function? What do we do to get rid of a y squared? We square root. So the square root of x over 2 is equal to y. So we do get plus or minus, which is not allowed. But we'll talk more about that later. And last step, f inverse of x is equal to plus or minus x over 2. So actually, I'll just tell you now while we're on this screen. So this one is not going to have an inverse unless we do something, because right now 2x squared looks like that. And if I flip it to this new blue one, I'm going to get something like this. And this is not a function. It's a square root graph. Do you recognize this little square root piece? But then it's also the minus square root. And it doesn't pass the vertical line test. So what I'm going to do is I'm going to restrict this domain. I'm going to say, you know what? Let's make that x is greater than or equal to 0. That way I can erase this section. And if I erase that section, then the inverse will end up erasing this section, and I will end up passing the vertical line test. So the correct answer would be this. But there is a spot later in your notes where I actually address that. Number 3 and 4, see if you can do them on your own. Step 1, replace f of x with y. Step 2, switch the x and the y. Step 3, solve for y. And step 4, write the function as f inverse. That's how we pronounce this, f inverse. And if you want to say of x, you can. Cube root of x plus 1. Minus 1. Minus 1. X minus 1 over 2. And the last one. Replace f of x with y. Switch your x and your y. Get y by itself. How do we undo a square root? We square both sides. That gives us x squared over 4 is equal to y minus 3. Y is equal to x squared over 4 plus 3, which our final answer would be f inverse is equal to x squared over 4 plus 3. Or you may like to write it as 1/4 x squared. Really knowing that 1/4 is the same as over 4 really trips people up. So I'm going to point it out as often as possible. All right, so this is a little section that I kind of introduced on example 2, which is that the inverse of a function is also a function if and only if no horizontal line intersects the graph of f more than once. So on number 2, we went to draw it, and we were like, oh, hold on, that plus or minus is going to mean it's not a function. It doesn't pass the vertical line test. So what these notes are saying is that you can actually know, even before you get the inverse, whether or not it's going to be a function. If something doesn't pass the horizontal line test, then its inverse won't pass the vertical line test. So right before you do anything, you can tell if something's going to have an inverse function or if you're going to have to do something to change it. So a cubic function no problem. You can draw any line. It's only going to hit in one spot. It passes the horizontal line test. But the parabola, as we saw, when you draw a horizontal line, does not pass the horizontal line test. And that's when you know that you're going to have to go back and make a little exception here so that you can get an inverse. That's a function. All right, last thing, verifying that two things are inverses. So to verify, we're going to compose the functions. And this is why we started the lesson with composition, because now you'll be really good at this. Use composition of functions to determine if they are inverse functions. So f of g of x. So f of, which is 3 times something minus 1. So whatever it's going to go in here is in place of the x. And what is going to go in there? X plus 1 over 3. The 3's cancel. So now I just have x plus 1 minus 1. And then I get x. And that answer is what tells you it is the inverse. Not just a inverse function. It is the inverse. So if you're trying to decide if something is an inverse function or not, you can compose them together. And sorry, that just does not want to write. You can compose them together. And if you get x, then you know that they're inverses. If f and g are inverse functions, then f of g of x is equal to x, or you could actually compose them backwards and you should still get x, which is what we'll do on the next one. So on the next one, I'm going to just to do it differently, I'm going to do g of f of x, and if they're inverses, it should still come out to be x. So g is something minus 5. What goes in there? X plus 5. And sure enough, x plus 5 minus 5 is just x. So yes, they are inverses. I will give you a little warning that if I say use composition of functions, then you have to use composition of functions. If I say use the graph, then you have to use the graph. The way you can tell on a graph is whether or not it reflects over the line y is equal to x. So we can test these two. 3x minus 1 starts there and goes up 3 over 1, up 3 over 1. And then this one is the same as 1/3 x plus 1/3. So I do have a slope of up 1 over 3, but I still need one good point. And what's a nice easy one? 2. If x is 2, 2 plus 1 is 3, 3 over 3 is 1. Always give yourself one good point. But I am going to give you a little shortcut hint. Think about this. If you found a point here, the point 1, 2, then 2, 1 should work. You don't even have to think that hard. And then from here, up 1 over 3, and then backwards. Do they reflect? Yes. So this is showing me graphically that they're inverses, where this process shows me algebraically that they're inverses. So this one's a little tricky. It was really easy to find the inverse algebraically, but it's a little bit different when you graph them. Watch what happens. 1, 2, 3, 4, 5, and it's just got a slope of 1. And then this one is x minus 5, and it has a slope of 1. And sometimes people think that they're not inverses because they're so used to them crossing. But remember, the only rule is that they have to reflect over the line y is equal to x. And they definitely do, above and then below. Okay, last one. So remember, if f of g of x is equal to x, or the other way around, it doesn't matter to me which way you do it, then we know that they're inverse functions. So f of 8 times something cubed, What am I going to put in there? The cube root of 2x. So now I have the cube root of 2x cubed. They cancel each other out, and I get 2x. Ooh, and I get 16x. So no, they are not inverses. And you don't need to try it the other way. If it didn't work there, it won't work. But just to practice your graphing skills, let's go ahead and graph these two. So 8x cubed means that instead of 0, 0, 1, 1, remember those are our main points, 0, 0, 1, 1, negative 1, negative 1, you have to multiply them by 8. So at 1, it doesn't matter to me that you can't reach 8. It just matters to me that you don't cross the 1 line. Because if you crossed it like that, that would indicate that 1, 3 was a point, and it's not. So just make sure that when you're graphing it, you don't cross that 1 line. And then cube root, this is a little bit harder, but you want to think of a number that when you multiply it by 2, you actually know the cube root. So, for example, ironically, 1/2. 1/2 times 2 is 1, and the cube root of 1 is 1. That might be hard to graph. Of course, 0, 0 is still there. But then the other one would be 4. 4 times 2 is 8, and the cube root of 8 is 2. So 0, 0, 4, 2, and we didn't actually do it, but negative 4 would produce negative 2. So this one wasn't so bad. But do you see how they're not inverses? Because if they had been, then this point, 4, 2, would have been 2, 4, and it's not going to make it. So they're similar, but they're not inverses. Okay, one final note, and that is sometimes on the test, I'll say to somebody, show that these are inverses. And what they'll do is they'll just find the inverse. They'll say y is equal to 8x cubed, x is equal to 8y cubed, x over 8 is equal to y cubed, y is equal to the cube root of x over 8, y is equal to the cube root of x over 2. And then they'll say, no, they're not inverses. That does show that they're not inverses. But if I specifically say use composition of functions, then you have to actually use composition of functions to show it. Do not do it by actually finding the inverse and seeing if you get the right answer. Just a little side note there. All right, that is it for section 5.6, which is also the end of the chapter. So great job. We've made it through chapter 5. Have a great day.